All right, predicting the outcome of acid-base reactions. If you know your pKa table and you have it memorized, and we've talked about that, memorizing these main groups, just memorize that whole dang thing. It is very useful. It turns out in acid-base reactions always favor the formation of the weaker acid and the weaker base. The good news is if a reaction forms the weaker acid, it will always form the weaker base also. So all you really need to look at is the acid in the reaction. We don't have to necessarily look at the base. All we really need to look at is in a Bronsted-Lowry reaction, the acid versus the conjugate acid. Now we could look at the base versus the conjugate base. I just like to look at the acid. Look at the pKa of the acid in the reaction, then look at the pKa of the conjugate acid as in the product of the reaction, and compare those two. The reaction will always favor the formation of the weaker acid. So if the conjugate acid is a weaker acid than our original acid, let's say that again, if the conjugate acid on the product side is a weaker acid than our original acid on the reactant side, then the equilibrium goes to the right. If the conjugate acid is a stronger acid than the original acid, then the equilibrium goes to the left. All right, because the weaker the acid and the weaker the base, the more stable they are. For example, let's look at this reaction here. Here we have a carboxylic acid. I put the R group there. Recall R just means the rest of the molecule, normal alkane part of the molecule. This carboxylic acid plus sodium hydroxide goes to this carboxylate ion plus H2O. Now, does this equilibrium go to the right or to the left? Now, you might have memorized from Gen Chem 2 that anytime you have a weak acid, recall carboxylic acids are weak acids, and a strong base, this reaction goes 100% to the right. Well, let's check that out. Here is our acid, pKa of 3 to 5. Which is the conjugate acid? Well, recall, the acid turns into the conjugate base, the base turns into the conjugate acid. Therefore, here's our acid, here is the conjugate acid. Let's look at the pKa's here. The pKa of carboxylic acids is about 3 to 5. The pKa of water is 15.7. So which is the weaker acid? pKa of 3 to 5, around 4, or pKa of 15? Well, pKa of 15 is the weaker acid. So we now know that this conjugate acid is weaker than our original acid. The reaction favors the formation of the weaker acid, so we know this reaction goes to the right. It's still probably a little confusing to you, so let's run through some examples and try to clear some things up. Okay. For example, let's take, I don't know, how about CH double or triple bond C dot dot minus Na plus H2C double bond CH2. And the question, one you might find on an exam, is what are the products of the reaction and does the equilibrium lie to the left or to the right? Well, let's take a look at this. What are the products of a reaction? Well, we know that even though we're looking at Bronsted-Lowry reactions, that the negative always is going to attack something positive. Well, what's negative and what's positive? Well, we definitely have this big negative thing here. Here's a little insider tip. Anytime you see a sodium ion, we know that that sodium cation is a spectator ion. It's not involved. So anytime you see the spectator ion sodium, We know it has positive charge. We know the thing that it is next to has negative charge. We know that's going to be the base. The fully negatively charged thing, the thing next to the sodium or a lithium or a potassium, any alkaline metal, which is a not involved in the reaction, spectator ion, anything next to that is going to be the negatively charged piece. That's going to be the base. So looking at that, we know that this lone pair here is going to be the base. This is the base right here. If that's the base, that means this is the acid. And we're looking at Bronsted-Lowry, so we're going to take a proton. So we could draw arrows, and FYI, I always like to draw my arrows in red. This lone pair is going to attack one of these hydrogens, and that bond is going to go onto the carbon. I didn't draw the bond here, but I just want to indicate that one of the carbon-hydrogen single bonds will become a lone pair on that carbon. So we will get, recall, this lone pair attacking this hydrogen means we get CH, because we originally had the CH. Triple bond, that didn't change, to this C, and now this carbon is single bonded to a hydrogen. Plus, we now have a lone pair on this carbon. It still has one H bonded to it, double bonded to this CH2, but we now know that this carbon has negative charge. Therefore, the Na is probably just hanging around here somewhere. So let's, where do we want to put the Na? Let's put the Na right in front here. And those are the products of the reaction. Note, this molecule here had the negative charge. Once it donated the electrons to the hydrogen, it took in H+, so this became neutral and this became negative. And so, well, this is our base. Recall, in Bronsted-Lowry acid-base reactions, the base becomes the conjugate acid. So if the triple bonding alkyne was the base, that means it is now the conjugate acid. If this was the acid, the proton donor, it is now the conjugate base. Well, which way does this equilibrium lie? Well, let's take a look. We need to compare the pKa of the acid with the conjugate acid. Well, pKa, this is our acid, our proton donor. We recall alkenes have a pKa of 44. Cool. Okay, here's our conjugate acid. It's an alkyne. We recall terminal alkynes have a pKa of 25. And so the question is, which is the stronger acid? Well, the lower the pKa value, the stronger the acid. The higher the pKa value, the weaker the acid. Note that this, with pKa 44, is a weaker acid than this. Higher pKa value, weaker acid. Lower pKa value, stronger acid. Well, which way do reactions go? Do they go to form the stronger acid or do they go to form the weaker acid? That's right, they go to form the weaker acid, which tells us this equilibrium, even though it is equilibrium lies to the left, towards the weaker acid. So what that tells us is if you take this stuff in this molecule here, mix it with this molecule here, you're mainly going to get a mixture of these two molecules. This equilibrium lies to the left. What it also tells us is if we take this terminal alkyne and mix it with this reaction will go nearly 100% to form these two things. This reaction goes this way to the left in this respect. Okay. Well, that took kind of a lot of work. Okay, let's do another one. Let's start with, our good friend again, HC triple bond CNA plus, and I'll write this out, CH3 CH2OH. What's the product of this reaction, or what are the products, and which way does equilibrium lie? And these are all going to be acid-base reactions. Ooh, just for fun, let's put on some lone pairs here. Cool. Well, what's going to attack what here? That's our first question. What is going to be the base? What's going to be the acid? The base has to take a proton from one of these things. What's the base going to take a proton from? Which is going to be the base? Which one's going to be the base? Well, we've got our hint. What's our hint to be as to telling us which is the base? The sodium. We know the sodium has positive charge. It's a spectator ion. We don't worry about it. Which means this carbon needs to have negative charge. How can a carbon with 3 bonds be negatively charged? If it has a lone pair and it is a carbanion, it is negatively charged. So we know that this is our negative charge thing because it had the sodium with it. This is going to be the base. If that's the base, then this guy's going to have to be the acid. This has to be the acid if this is the base. Okay, but I see lots of hydrogens. The question is, which hydrogen is the base going to take? Well, the answer is the hydrogen that has the lowest pKa value. The hydrogen that gets taken, another way of saying that is the hydrogen that gets abstracted, is the hydrogen with the lowest pKa value. Because the lower the pKa value of the hydrogen, the more acidic the hydrogen is. The more acidic it is means the more likely it is to be given up. So we need to look at these hydrogens, and what do we notice? Well, this is just CH3 and CH2. This is kind of normal alkane type stuff. What are the pKa's of these hydrogens right here? Recall from the table, normal alkane, the pKa of these hydrogens is around 50. Which is not very acidic at all. Oh, but what's this guy out here? Here's this hydrogen on oxygen. We recognize that's an alcohol. What's the pKa's of alcohols? Well, 16 to 18. So let's go with a pKa of 16 here. So which hydrogen is the most acidic? This hydrogen is the most acidic. So we know that this is our base, this is our acid, and the most acidic hydrogen on that acid will be the one that gets taken, this one right here. So I can draw my red arrow. I know that this lone pair will attack this hydrogen, and this bonding pair between this oxygen and this hydrogen will become a lone pair on that oxygen. So I now know my products of reaction. This forms a bond to that hydrogen, so I get HC triple bond CH plus, we got a lone pair on here, that oxygen, so I get CH3, CH2, nothing happened to them. This bond is still there. Note, the arrows tell me about movement of electrons. The electrons aren't going anywhere here or here. So all I know is this oxygen now had its 2 lone pairs originally. It's got a 3rd lone pair from that single bond. This left is H+, therefore this is negatively charged, and my sodium is hanging around here just watching the whole reaction occur. So, there we go. Well, does this equilibrium lie to the left or to the right? Well, let's see. Here we know this was our acid. We figured that out because this was our negative beast, which is a conjugate acid. Well, recall the base gets turned into the conjugate acid. The acid gets turned into the conjugate base. So here's my acid, here's my conjugate acid. I need to compare their pKa's. Good news. We already figured out the pKa here is 16. And what's the pKa here? Well, this is an acetylene. We have our table memorized, don't we? That the pKa of a terminal alkyne is 25, which is the weaker acid, because we know the equilibrium favors the weaker acid. Larger pKa, weaker acid. We know the equilibrium goes to the right. Equilibrium lies to the right here. Cool. Hey, you want to do another one? Why, of course you do. All right, so let's look at this. How about, for example, let's look at CH3COONA plus CH3CH2OH. What are the products of this reaction? Which way does the equilibrium lie? Well, first question, which is going to be the base? Hopefully you saw, okay, here's our sodium, which tells me this oxygen is negatively charged, which means it has an extra lone pair of electrons on it. This is going to be the base right here. What's it going to attack? Hopefully you see that the negative lone pair will attack this hydrogen here, since it is the most acidic hydrogen, just like it was up here. That bond breaks. And so our products are going to be, okay, CH3, got that. We bonded to that H, COOH, a carboxylic acid, plus CH3CH2ONA. We know our Na is positive, so we know this oxygen's negative, and it's got 1, 2, 3, 4, 5, 6 electrons around it, 3 lone pairs. All right. So, okay, which is the acid? We recognize this is the base, so this has to be the acid. The acid forms the conjugate base, so CH3CH2OH forms CH3CH2ONA, the conjugate base. This must be the conjugate acid. Look at the pKa's. This is an alcohol, pKa of 16. This is a carboxylic acid, pKa of around 4 to 5. So let's just put 4, that's a nice number. Which is the weaker acid? Larger pKa, weaker acid. This equilibrium lies to the left. Okay. So as you are working through these, here's a couple more to try. What would happen if, for example, you reacted CH4 plus NaOH? What are the products? In which direction does the equilibrium lie? What if you reacted, for example, CH3CH2OH plus NaH? What are the products, and which way does equilibrium lie? For example, what if you reacted CH3, CH2, CH2, CH2OH plus NaOH? What are the products, and which direction does the equilibrium lie? Work on those. Work on those on your own. And if you have questions, probably in lab, we can go through these.